Let us see the next question on the zigzag traversal of the tree. Now, what is zigzag traversal of the tree? Suppose I write tree, any tree, it might be binary tree or binary search tree, we don't care. If the tree is 10, 20, 30, here I say 40, 50 and 60, 70, and suppose here I write 80 and suppose here I write 90. Suppose this is a tree. Now you have to print this tree in zigzag order. Now what do I mean by zigzag order? First you have to print from right to left, then you should go this way, then again you should come this way, then again you go this way. Are you getting it? It's a kind of zigzag. Now the first thing what is being printed is 10. The next thing is 20, 30. The next thing is 70, 60, 50, 40. Therefore I say 70, 60, 50, 40. And what is the last thing that is being printed? 80 and 90. This is zigzag traversal. Now you can observe one thing, that they are printing level by level. Hence level order traversal has to be preferred. Fair, good enough. Level order traversal has to be preferred over here. Now if you observe another thing, level 0 we are printing from right to left. Level 1 we are printing from left to right. Again level 2 we are printing from right to left. Level 3 we are printing from left to right. That means each level, the way of printing is either left to right or right to left. It depends on the level. Alternate. First you say left to right, then you say right to left. Now how do we take care of this in the algorithm or program? We will use one variable called as flag. If the value of flag is 0, it means you have to print from RHS to LHS. This is our convention. You can change the convention as well. And if the value of flag is 1, it means you have to print from LHS to RHS. Is that okay? I hope this is understandable and this is fair enough as well. Now, since we know that it is a level order traversal, we need a queue data structure. Let's take the queue data structure. Now, what should be the initial value of flag? We are printing from right to left and the value of flag is 0. Therefore, I write here the initial value of flag is 0. Now, what is the level order traversal of the tree? Enqueue the root. What is root? Of course, it is address. Let me, as of now, let me enqueue only 10. Of course, it is the address of 10, 1000, 5000 and something. And we enqueue null as well. Can anyone say why do we enqueue null? Yes, we have solved this already. We enqueue null because it marks the end of the label. It says that 10 is in one label. Is that okay? Now what we do while the queue is not empty, we dequeue an item from the queue. Now what is the item from the queue you dequeue? You dequeue 10. Now as soon as you dequeue 10, we don't print immediately. Are you getting it? We don't print immediately. Why we don't print immediately? Answer is here. Now when you need from LHS to RHS, in the queue, it will be 20 and 30 as it is. Therefore you can print 20 and 30 as it is. But when you come from RHS to LHS, it will be in reverse order. It will be in reverse order. And which data structure is used to view the elements in reverse order? It is the stack data structure. Therefore, we need one more data structure, that is the stack data structure. It means if the value of flag is 0, you want to reverse in reverse order of the label. Therefore, if flag is 0, you simply push the value of u, that is 10. Of course, it will be the address. Of course, that will be the address. You don't print immediately. Next you check, does 10 has the left child and right child? Yes, it has left child and right child. It is 20 and 30. While the queue is not empty, dequeue an item. What is the item that we dequeue? It is null. Now, if it is null, it marks the end of label. Is that okay? Therefore, empty the stack and print it. Whenever you reach null, empty the stack and print it. You get 10. I am circling over here. You print it. Is that fair enough? Now, after you dequeue the item and print, negate the flag. Why negate the flag? Because you have printed from LHS to RHS. Now you want to print from RHS to LHS. Therefore, negate the flag. The value of flag will become 1. Now, after you negate the flag, you have to enqueue the null back if necessary. If necessary means if the queue is not empty. Is that okay? Now, again you go, queue is not empty. Yes, you dequeue an item from the queue. What is the item from the queue? 20. Now, when you dequeue 20, the question comes, shall we print or shall we push on stack? Now, what is the output you need? You need 20 and 30. Queue had 20 and 30. That means no need to reverse the alter of this level. Therefore, print 20 as it is. Yeah, we have printed 20 as it is. Now check 20 has, now that means if the value of flag is 1, do not push. If the value of flag is 0, then only push. What is the left child of 20? It is 40, and what is the right child? It is 50. Fair enough? Now again dequeue the item from the queue. What is the item from the queue? You dequeue 30. What is the value of flag? 1. Therefore do not push it. You print 30 arrow data, 3000 arrow data, whatever it is, 30. Now again you check the left child and right child of 30. What is it? It is 60 and 70. Therefore you enqueue 60 and you enqueue 70. Again you say u is equal to dq. What do you dq from the queue? You dq null from the queue. Okay, whenever you get the null, empty the stack and print it. Stack is already empty, leave it, nothing to be done. Negate the flag, therefore the value of flag becomes 0. For the next level you have to print from RHS to LHS, fair enough. And enqueue the null if the queue is not empty. Yeah, queue is not empty, enqueue the null. Great. Now 40, 50, 60, 70 are in one level. Now again dequeue an item from the queue. What is the item from the queue? 40. Now check. What is the value of flag? 0. Therefore do not output it. Push 40 onto the stack instead. Now check for the left child and right child of 40. It is 80 and there is no right child. Therefore you enqueue 80 onto the queue. You enqueue 80 onto the queue. Fair enough? Now again you say u is equal to dq. You get 50. Now when you get 50, again the value of flag is 0. Therefore push it on the stack. You get 50. Now does 50 has any left child and right child? No left child and right child. Therefore do not enqueue. Again you say u is equal to dq. What do you dq? You dq 60. The value of flag is 0. Therefore enqueue 60. Push 60. I'm sorry. No left child and right child. Therefore do not enqueue anything. Now you dq. What do you dq? You dq 70. Again the value of flag is 0. Therefore you push 70 onto the stack. Does 70 has left child? Yes, it has left child. And what is the left child? 90, and there is no right child. Therefore you leave it. Again you say u is equal to dq. What is the dq? Null. Now whenever it is null, empty the stack and print it. What is the stack? 70, 60, 50, 40. Okay. Now the stack has become empty. Fair enough? Negate the flag. Flag equal to 1. Now enqueue null if necessary. If necessary means queue is not empty. Yes. Therefore you have enqueue null. Queue is not empty. Yes. You dq. What is the value of dq? 80. Now if the value of flag is 1, no need to push. You simply print 80. Does 80 have left child and right child? No left child and right child. Therefore do not do anything. Next again you say u is equal to dq. What do you dq? You dq 90. Print 90. Does 90 has left child and right child? No. When we print 90 again, the value of flag is 1. Now you say u is equal to dq. What is the value of dq? Null. Now whenever it is null, empty the stack and print it. Stack is already empty. Negate the flag. Therefore the value of flag will become 0. Enqueue null if the stack queue is not empty. Now queue is already empty. Therefore do not enqueue it. And you stop the procedure and you see that the the zigzag order traversal of the tree is being printed. Is that okay? Before I write the code, I want you to pause the video and try yourself writing the code with the algorithm whichever I have explained. Please try it before I write the code. Thank you. Let us write the code for it. First we need to write the case. I am writing case here. Case whatever is the number you see. Next what do I write? I say zigzag and we pass the root. We don't need ampersand root because the value of root does not change. And what do I say? I say break. Okay. Now let us write the code for the zigzag order traversal of a tree. We say void. What is the function name? Zigzag. What is the first parameter? Root. Therefore I say struct node star root. Is that okay? Now again if the value of root can be processed, we cannot process. Therefore we have to check here itself if the value of root is equal null, then we return because there is no zigzag over here. Now we need two data structure, one is queue, one is stack, both are of the node pointers, and if you want, let me give the addresses as well. Let us say 1000, 3000, 5000, 2000, and the addresses are assumed randomly, we know that. Suppose these are the addresses on this we want to print. What do? We enqueue the root and null onto the queue. And we have to create a queue. Let us say struct queue. Now this is not an empty queue. This queue has to be initialized. Hence we say init queue of ampersand queue. And we need one more data structure. This is the stack data structure. And this stack data structure also has to be initialized. And what do I write? I say struct stack yes. And what do I write over here? I say init stack of ampersand yes. Now the stack is also initialized. Fair. And we need one variable called as flag so that we know if it is left to right or right to left. Already I explained. Flag equals 0 means right to left. Okay, I write here in comments 0 is right to left and 1 is left to right. This is for your reference. This is in part of the comment. And whenever you now the first thing is you have to enqueue it. Therefore, let us enqueue. I say enqueue. In this queue, what do we enqueue? We enqueue the root. Now, what is the value of root? The value of root is 1000. 1000 is enqueued. Now, you have to enqueue null as well to mark the end of the label. We say enqueue ampersand q comma null. What will be enqueued? Null will be enqueued. Fair enough. And we need one variable so that whenever we pop, we need it. Therefore, I write a struct node star u. Therefore, I write struct node star u. Now, till how long we should process? Till the queue is not empty. Hence, I write while not is empty of queue. While not is empty of queue. Yes, queue is not empty. You need to dequeue an item from the queue. And that's very simple. You say u is equal to dequeue. Now, whenever you dequeue, there are two possibilities. Yeah, I have dequeued 1000. There are two possibilities. Either the value of u is null and the value of u is not null. If the value of u is null, it marks the end of the label. Yes. Therefore, I write here if u equal null, what it does, it will mark the end of the label. And if it is the end of the label, I need to do something. Now, as of now, the value of u is 1000. Now, 1000 equal to null? No. Therefore, we come to the else part. It is not null. If it is not null, we have to push 1000 or we have to print the data depending on the value of flag. If the value of flag is 0, it is RHS to LHS. Already I said. Hence, we check. If the value of flag is equal 0, what do we say? We push in the stack yes. What do we push? We push u. What is the value of u? The value of u is 1000. Now suppose the value of flag is 1. That means you have to print the data then and there. Therefore, what do I say? I say else print u arrow data. Else print u arrow data. Now to begin with, the value of flag is 0. 0 equal 0 is yes. Therefore, you push it. Now you check. Does 1000 has the left child and the right child? How do we write it? We say if u arrow left not equal to null. Now what is u arrow left? 1000 arrow left is 4000 not equal to null. Yes, it is not equal to null. Therefore, we say enqueue ampersand q comma u arrow left. Now what is the value of u arrow left? 1000 arrow left is what? 4000. 4000 is enqueue. Next you have to check, is there a right child? How do we write? If you say if u arrow right not equal to null, then you write down complete enqueue. I just say enqueue. Enqueue of, what do I have to enqueue? U arrow right. Okay, this is the end of else, this is the end of while, and this is the end of function. What is u arrow right? 1000 arrow right is 3000. Okay, go back. Q is not empty. Yes, Q is not empty. U is equal to dq. What do you dq? You dq null. Is null equal null? Yes, null equal to null. Marks the end of the label. Whenever it is the end of the level, empty the stack and print it. Now, how do we empty the stack? We say while not is stack empty. You cannot take is empty function because is empty function we have taken it for q. You rename the function with respect to stack as while not is empty of stack. The stack is not empty. What we want to do, we pop an item from the stack and print it. Now when I say pop of print, you have to say print, okay, printf percentage %t. When I say pop of ampersand, yes, what do you get? You get 1000. Do you want to print 1000? No, I am interested in data. Therefore you say pop of ampersand, yes, arrow data. Therefore 10 is printed on the output screen. I am writing over here. Is that okay? Again go back, not is empty of stack is false. Now we have to negate the flag. The value of flag should become what? 1 from 0. And how do we negate the flag? You say flag is equal to not flag. Now flag is 0, not of 0 is 1, therefore the value flag becomes 1. Now you have to enqueue the null only if the queue is not empty. Therefore we check here if not is empty of queue. What we should do? We should enqueue, write completely enqueue. In this queue we enqueue null. Yes, queue is not empty, we enqueue null. Is that okay? Since if has executed, else should not execute, go back, queue is not empty, yes, queue is not empty. U is equal to dq. What do you dq? You dq 4000. Now is 4000 equal null? No. Flag equal to 0? No. You print 4000 arrow data. What is 4000 arrow data? It is 20. 20 is printed. Right? Now you check 4000 arrow left. What is 4000 arrow left? Null. 4000 arrow right is not null. Therefore, you enqueue 2000 onto the queue. You enqueue 2000 onto the queue. Fair enough? Go back, queue is not empty. Yes, u is equal to dq. What do you dq? You dq 3000. Is 3000 equal to null? No. Flag equal to 0? No. Print 3000 arrow data. What is 3000 arrow data? 30. What is 3000 arrow left? It is 5000, not equal to null. Therefore, you enqueue 5000. Fair enough? 3000 arrow right is null. Do not enqueue. Go back. U is not empty. Yes, u equal to dq. What do you dq? You dq null. We dq null. Is null equal to null? Yes. Not is empty of stack. Stack is already empty. What do? You do nothing. Therefore, this loop does not execute. Flag equal to not flag. Therefore, the value of flag becomes 0. Fair enough? Not is empty of q. Yes, q is not empty. Therefore, you enqueue null back. Again go not is empty of q. Yes, u is equal to dq. What do you dq? You dq 2000. Okay. Is 2000 equal to null? No. Flag equal to 0? Yes. Therefore, you push 2000 onto the queue. Now 2000 arrow left is null, 2000 arrow right is null. Do not enqueue. Go back. Not is empty of q. Yes. U is equal to dq. What do you dq now? You dq 5000. Is 5000 equal to null? No. Flag equal to 0? Yes. You push 5000 onto the stack. Okay. U arrow left, 5000 arrow left is null, 5000 arrow right is null. Do not do anything. Go back, not is empty of q. Yes. U is equal to dq. What do you dq? You dq null. I'm sorry. Flag is 0, you dq null. Null equal to null, yes. Stack is not empty, yes. Stack is not empty. Pop of ampersand, yes. It is 5000. Pop is 5000. Now what is 5000 arrow data? 5000 arrow data is 60. Therefore 60 is printed. Not is empty of stack, yes. It is 2000. 2000 arrow data is what? 50. 50 is printed. Stack is empty. Flag equal to not flag. Flag becomes 1. Not is empty of q. Now the q is empty. Therefore do not enqueue. Again go back. Not is empty of q is false. And you see this is the zigzag traversal of the tree. I hope you have understood it. Next, let us see the next question on the mirror of the tree. Thank you.